Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 31st, 2025, just 2 days ago. It introduces a new framework that significantly improves the physical realism of AI-generated videos, achieving scores 4.5 times higher than the baseline on complex action benchmarks. The paper is titled PhyGDPO, Physics-Aware Group-Wise Direct Preference Optimization for Physically Consistent Text-to-Video Generation. And as we'll see later, the results are really impressive, offering a way to make videos not just look good, but actually behave according to the laws of physics. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 highlights the physics gap by comparing generated videos in 4 scenarios: gymnastics, soccer, basketball, and glass smashing. Standard models, shown in the outer columns, often fail at basic interactions, like a foot missing the soccer ball or a body bending unnaturally. However, the center columns display the proposed PhyGDPO method. It successfully enforces physical laws, ensuring the basketball cleanly enters the hoop and the glass shatters with realistic debris distribution, outperforming even commercial tools like Sora 2. Figure 2 details the data construction pipeline, called PhyAugustPipe. It begins on the left with a large pool of raw text-video pairs. A vision language model uses chain-of-thought reasoning to filter out cartoons, keeping only clips with rich physical phenomena like those in the green boxes. The middle section then clusters these clips into action categories. Finally, on the right, a physics-aware model scores the difficulty of these actions to prioritize the hardest scenarios for the training set. Next, Figure 3 outlines the complete training framework. On the left, Panel B introduces a low-rank adaptation switch reference scheme. This component toggles between trainable and fixed weights to significantly reduce memory usage. The core innovation appears in Panel C, detailing the group-wise optimization. Here, a physics vision language model evaluates a whole set of videos at once. It compares multiple generated clips, shown in the blue box as losing samples, against a real video in the red box, which serves as the winning standard. This group approach captures more holistic preference signals than standard pairwise methods. Table 1 breaks down the quantitative performance gains, validating the method against top-tier competitors. In the first panel on the left, covering the video Phy2 benchmark, PhyGDPO achieves the highest overall score of roughly 0.16. Crucially, it outperforms commercial models like Google Veo 3.1 and OpenAI Sora 2, even on the challenging hard subset. The middle panel details physical properties on PhyGeneral Bench, showing consistent leads in mechanics and optics. Finally, the user preference study on the right confirms this advantage, with human raters favoring the proposed model over Sora 2 about 67% of the time. Figure 7 offers a visual ablation to show exactly how these gains manifest. The top row, Panel A, tracks a tennis ball placed in water. As we move right from the baseline, adding the LoRa switch reference, group-wise modeling, and physics-guided rewarding incrementally improves the simulation, until the ball correctly floats according to buoyancy laws. In the bottom left, Panel B compares weightlifting generations. While Video DPO and Flow DPO distort the athlete's body, the proposed method maintains a coherent physical structure. Finally, Panel C on the bottom right demonstrates that the LoRa switch reference alone significantly refines contact points like the hands gripping a snow shovel. Table 2 provides the hard numbers behind those visual improvements. The top panel breaks down component contributions on the WAN 2.114b model. Starting from the baseline, every addition, including the group-wise model and physics rewarding, steadily climbs the metrics, quadrupling the hard score by the end. The bottom panel then highlights efficiency. Compared to training without it, the LoRa switch reference cuts GPU memory usage almost in half, from 49 GB to 25, and compresses storage needs from 5 GB down to just 84 MB. To wrap things up, the big takeaway is that PhyGDPO effectively teaches video models to follow physical laws, rather than just mimicking textures. By combining group-wise optimization with a physics-rich dataset, it moves generative video much closer to becoming a reliable, real-world simulator. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.